Today, we're pulling back the curtain on something we all see but rarely think about: satellite images. We're going to follow the incredible and mostly invisible journey from a messy, raw signal zipping through space to those stunningly clear pictures of Earth that we rely on every single day. So let's dive in. I mean, you've probably wondered about this, right? We see these perfect, map like views on our phones, on the news, and we just kind of take them for granted. But is that really what the satellite is sending down to us? Yeah, not even close. The image on the left, that's the polished, final product we all know and love. But the journey actually begins with something that looks a lot more like the mess on the right. It's a noisy, distorted signal packed with errors, like all that weird horizontal banding you can see. So how on earth do you get from that mess to this masterpiece? Well, the answer is a hugely important step called pre-processing. Honestly, you can just think of it as the digital cleanup crew for satellite data. It's this whole collection of really clever techniques designed to fix all the problems in the raw signal, getting it ready before anyone can even think about analyzing it. Okay, so first things first, we've got to fix all those ugly flaws and glitches. The source material actually calls this the cosmetic surgery for data, which I think is a perfect way to put it. It's all about fixing those obvious visual problems that just jump right out at you. Here's a classic example: a dropped scan line. And it is literally what it sounds like. It's a black line right across the image where an entire row of data was just lost. Maybe a hiccup in transmission, but either way, a whole line of information is just gone. So, how do you fix that? I mean, the data is gone forever. It's not like you can just call up the satellite and ask it to send that bit again. So, how in the world do you fill in that black hole? Amazingly, we can, and we do it using a principle called spatial autocorrelation. Now, that sounds super technical, I know, but the idea behind it is incredibly simple. It just means that things that are close to each other on the Earth's surface tend to look similar. You know, a pixel in the middle of a forest is probably going to look a lot like the pixel right above it. And that predictability, that's the key. So we use that simple idea to make a really, really good guess. The most common fix is just what you see here. The computer looks at the pixel directly above the empty spot, the one directly below it, averages their values, and boom, fills in the blank. It sounds almost too simple, but it works surprisingly well. Okay, so the other big cosmetic issue you see all the time is this thing called banding. See, satellites like Landsat don't just have one big camera. They have a whole array of detectors scanning the Earth side by side. And if just one of those detectors is a tiny bit out of sync with its neighbors, you get this repeating pattern of light and dark stripes across the whole picture. The fix for this is all about statistics. The software is smart enough to analyze the data coming from each individual detector. It figures out the unique profile for each one, like its average brightness, and then it just adjusts them all so they match. It's this clever digital balancing act that just makes the stripes completely vanish. All right, so we've done the cosmetic surgery. The image is looking a lot cleaner, but there's a huge problem. It is still not a map, not even close. So the next giant step is to fix the image's geometry so it actually lines up with the real world. In this quote right here, it absolutely nails the core concept. Remotely sensed images are not maps. You have to get this in your head. A raw satellite image is just a picture. A map is a precise, geographically accurate tool, and that is a world of difference. So why isn't it a map? What's the problem? Well, it turns out there are a whole bunch of different forces at play that literally twist and warp the raw image, bending it completely out of shape. And here is one of the biggest culprits: the Earth's rotation. Think about it. The satellite is flying south in a nice straight line, but the planet is constantly spinning east underneath it. So each new line the satellite scans is just a little bit offset from the one before. What you end up with is this classic skew effect that distorts the whole image. This table really gets to the heart of it. A raw image just thinks in terms of columns and rows. You know, this pixel is at row 100, column 50. It has no idea where it is in the real world. A map, on the other hand, uses a coordinate system like latitude and longitude that tells you exactly where something is on the globe. The whole point of this next step is to transform that simple pixel grid into a proper map grid. Okay, so how do you do that? How do you pin this floating, distorted image down to the real world? Well, you need anchors. And in remote sensing, these are called ground control points, or GCPs. They are the absolute key. They're just common reference points that you can find in both the skewed image and on a perfectly accurate map. And what makes a good anchor point? Something permanent, sharp, and easy to pinpoint. A crisp road intersection is perfect. So are the corners of airport runways or the edge of a dam. What you don't want is something that moves or changes, like a river bend or the edge of a forest. You need solid, unchanging features. And this is basically what that process, called registration, looks like in the software. You identify dozens of these GCPs all over the image, and you tell the computer, see this intersection in my image? Well, it's supposed to be at these exact map coordinates. Once you do that enough times, the software calculates the exact math needed to stretch, rotate, and warp the raw image until it fits the map perfectly.
Okay, we're almost there. Our image is clean and it's geometrically correct. But there is one final hurdle we have to clear. We have to account for the atmosphere itself, for all the light and haze the signal had to travel through to even reach the satellite.
You know, the atmosphere isn't perfectly transparent. It can scatter light, which makes things look hazy, or it can absorb light, which makes them look darker. Plus, the angle of the sun creates shadows that can hide things. For any real scientific work, like comparing images over many years to track deforestation, you have to mathematically remove all those atmospheric effects to get a true, consistent measurement of what's really happening on the ground. So, after all that, all the fixing, the stretching, the correcting, what was the point? Why does this entire hidden journey of pre-processing matter so much? Because without it, the data is almost useless. Once it's corrected, you can drop that image into a geographic information system, and it'll line up perfectly with road maps or property lines. Scientists can finally compare images from different years and reliably track things like urban growth. And ultimately, this whole process is the hidden foundation of the maps we all use on our phones every single day. And that right there is the big takeaway. Pre-processing is the unsung hero of remote sensing. It's that complex, absolutely essential process that transforms a noisy, distorted signal from space into a reliable, accurate, and powerful piece of information about our planet. So the journey is complete. We've gone from raw signal to a perfect picture. The data is now clean, accurate, and ready to be explored, which leaves us with the most exciting question of all. Now that the image is corrected, what stories can it tell?